we have an example problem here. A 1.2 meter long string is fixed at both ends and tightened until the wave speed is 40 meters per second. What is the frequency of the standing wave shown in the figure? All right, so they're showing us a standing wave pattern. The way they're showing it is representing where these antinodes, how we would see these oscillating up and down. Okay, we're given the length of the string and we're given the speed. With standing waves, the length of the string is always related to the wavelength. If I start at one end and trace the wave and count how many wavelengths I have. So this would be one wavelength to there, and then two wavelengths, and then half. So I'm seeing 2.5 wavelengths on this whole string that has a length L. So 2.5, that would be 5 halves wavelengths. So I can say that the wavelength of this particular pattern that we're seeing is 2L over 5. Now you can also, if you remember the number of antinodes, there's 5 antinodes here, m is 5, we can totally use the equation that the wavelength of the mth harmonic is 2L over m. We get to the same place. I like to reason it out counting my wavelengths, because that I can always do just fine. So since we know the length of the string, this will give us the wavelength of this specific wave. So the wavelength of this specific wave on this string is 0.48 meters. We've been given the speed. Well, we know the speed of a wave is wavelength times frequency. So the frequency of this wave will simply be the speed over the wavelength. So 40 meters per second divided by our 0.48 meters gives us 83 meters per second. And just kidding, oh, good grief. Sorry about that. My meters cancel. This gives us hertz. So 83 hertz is the frequency of this standing wave shown here.